Our next talk will be from Dave. Dave is a semi-retired software development consultant with 39 years of experience. In his talk, Dave will introduce the concept of mutation testing. He'll explain how this technique can reveal problems with your code and tests. They will also equip the audience with a powerful tool for ensuring code quality. Ladies and gentlemen, please give a warm welcome for Dave.
Zdravo Beograde. Yes, but wait, there's more. Ja sam Dave Aronson, Tyrannosaurus rexis Kodosaurusa, I doleteo sam ovde, nazvam pterodactylo, da vas naučim kako da ubijete mutante. Ali, uradit ću to na engleskom. So let's start with the very basics. What makes mutation testing, on one hand, different from all the other software testing techniques we know? The big difference is that most of the others are about checking whether or not our software is correct. But mutation testing assumes that our software is in fact correct, at least in the sense of passing all its tests. Instead, mutation testing is checking for two other qualities. And I think in a typical code base, the more important of these two is that our test suite is strict. And to check this, a mutation testing tool will try to find the gaps in our test suite that let our code get away with unintended behavior. When we find these gaps, we can fill them in by either adding more tests or by expanding some existing tests. Lack of this strictness usually comes from lack of tests, of course, or poorly written tests. The other thing that mutation testing forgot to show that slide. Okay. The other thing mutation testing checks for is that our code is meaningful, so that any tiny little semantic change to the code will have a noticeable effect on its behavior. Lack of meaning usually comes from code being redundant or unreachable or otherwise just not having any real effect. And when we find such code, the usual fix is to just remove it. Pretty easy. Mutation testing puts these two together to check that every tiny little change the tool knows how to do does indeed have a noticeable effect on the code's behavior, and that our test suite is strict enough that at least one test will notice that change and fail. Now, that's the positive side, but as Fred Brooks told us back in 1986, there's no silver bullet. Besides, those are for taking care of werewolves, not mutants. The first drawback is that it's rather hard labor on the CPU, and therefore usually rather slow. We certainly won't want to mutation test our entire code base every time we save one file. Maybe over a lunch break for a smallish system, or over a weekend for a fairly large one. Fortunately, most of the tools have ways to tell them, I only want you to check this function, this module or class or whatever, or this file, or perhaps a few files, a directory or something. And many of them even have some kind of incremental mode. So you can tell them, only check what changed since the last time we ran the tool, or the last git commit, or the difference between this and the main branch. With filtering like that, maybe we can check just the relevant changes when we save a file, or at the very least, over a much shorter break. Another drawback is that it's often not at all clear what to do about the results. A mutation testing tool will tell us that this particular change to the code made no difference at all to the test results. But what does that even mean? It can take a lot of effort to figure out exactly what a surviving mutant is trying to tell us. they're usually trying to tell us that our code is meaningless or our tests are lax, or both, but it can be very hard to figure out exactly how. So now that we've seen some of the pros and cons, what exactly does mutation testing do? It mutates copies of our code, hence the name. And it does this in order to create test failures, otherwise known as faults. So mutation testing can be categorized as a fault-based testing technique. This means that it's related to something you might already be familiar with, Chaos Monkey from Netflix. But the way mutation testing works is sort of upside down from what Chaos Monkey does. Chaos Monkey is best known for injecting faults into Netflix's production network. If all still goes well, in the sense that Netflix's customers don't notice and their metrics still look good, then Netflix knows that their error recovery is working fine. Mutation testing, however, injects semantic changes, not necessarily faults. We hope each of these changes will cause faults, but that depends on the test suite. That's kind of the point. It injects them into copies of our code, not our actual network, and it does this in our test environment, not production. And if all still goes well, in the sense that our tests all still pass, that does not mean all is well. That means that there is a problem. Remember, every change should make at least one test fail. So how does mutation testing do all this? First, the tool will break our code apart into pieces to test. Usually these will be our functions, or methods if we're using object orientation, but I'm just going to say functions. Then for each one, it tries to find the tests that cover that function. If it can't find any, then usually most of them will skip that test and ideally warn us, so we know we need to add or maybe annotate some tests. On the other clause, some of them will use the whole test suite, which is horribly inefficient, of course. Then the mutation testing tool will make mutants from the function, assuming we're not skipping it, of course. And to do that, it'll look closely at this function to see how it can be changed. And for each tiny little way it sees to change that function, it will make one mutant with that one mutation. Once our tool is done creating all the mutants it can from a given function, it then iterates over that list. And now we get to the heart of the concept. This chart represents the progress of our tool. Unfortunately, most of them don't give us quite all this information, let alone so nice and neatly organized, but it's a useful conceptual model. For each mutant derived from a given function, the tool will run the function's tests, but it'll run it using the current mutant instead of the original function. There we go. Oops. Well, if any test fails, this is called killing the mutant, and it's a good thing. It means that our code was, in fact, meaningful enough that the tiny little change the tool made in order to create this mutant did indeed have a noticeable effect on the code's behavior, and that our test suite is indeed strict enough that at least one of its tests would notice that change and fail. Then the tool will mark that mutant killed, stop running any more tests against it, and move on to the next one. Once a mutant has made one test fail, we don't care how many more it might make fail. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the tests pass, then it is said to have survived. And this means that it has the superpower of mimicry, skilled enough to fool our tests. This usually means that our code is meaningless or our tests are lax, or both, and now it's up to us to figure out exactly how. Now let's peel back one layer of the onion and look at some technical details of how this works. First, our tool parses our code into an AST. Some of the ones that are not really ready for prime time, like experimental ones and so forth, work on the actual source code or in between, maybe bytecode, but the vast majority of the ones in actual use will use an AST. Next, the tool will traverse that AST, looking for smaller subtrees, or branches, if you will, that represent our functions. And for some of the tools, finding the tests will require that we developers annotate our code, well, at least our tests, or follow some naming convention. Some of the smarter ones, though, can look at what tests call what functions coming out of our code base. Those will typically gather that information by running your test suite as normal once and look at the coverage data. Now, to make the mutants from that little AST subtree that represents one function, it will traverse that little subtree just like it did to the whole thing. But this time, instead of looking for even smaller subtrees it can extract, like maybe twigs or something, it's looking for nodes where it can change something. And when it finds one, then for every way it sees to change that node, like changing it from a multiplication node to a division node, or swapping the operands of a minus node, or whatever, then it will make one fresh copy of that function's AST subtree with that one node changed in that one way. In other words, again, one mutant with that one mutation. Now, I've been talking a lot about changing things, so what kind of changes am I talking about? There are quite a lot. It could change an operator from one to another. It could swap the order of the operands, as I mentioned a moment ago, in cases where it matters. Of course, if you do that on a plus node or something, that's not going to do anything. It could change a comparison from one to another. It could insert or remove a negation. It could remove an if condition, or, taking that a step further, a looping condition. It could replace a function's entire body with something like returning some constant or one of the arguments, or raising a deliberate error, or nothing at all when the language permits. It could change a value to some other value, like changing a 42 to any of these constants or expressions, and many more, but I had to stop somewhere. You could even change it to something of a completely incompatible type, like changing a number to a, if I may quote Smeagol, string or nothing. There are many more, but I trust you get the idea by now. So let's now finally walk through some examples. And we'll start with an easy one. Suppose we have a function like so. Never mind why, it just makes a good simple example, so let's roll with it. Think about what a mutant made from this might return. Since that's what our test would almost certainly be looking at, it sure doesn't look like it would be having side effects. Mainly, it could return something like any of these expressions or constants, and once again, many more, but I had to stop somewhere. Now suppose we had only one test, like so. Now this is a rather poor test, and I think at least one reason why is probably rather obvious to most of you. But even so, the vast majority of these mutants, the ones crossed out here crossed out in green, would get killed by that test. The ones returning constants are very unlikely to match. There's no particular reason a tool would put a 4 there as opposed to 1, 0, -1, plus and minus infinity, the largest and smallest signed and unsigned integers of various sizes, and on and on and on, and other such significant numbers. If it changed the Exponentiation into subtraction, that gets us 0. Making it division gets us 1. And returning either argument alone gets us 2. And the mismatched types and deliberate errors will at least make the test not pass. But addition, multiplication, and exponentiation in the reverse order all get us the right answer. So mutants based on those mutations will survive our current test suite. This is the usual way mutants survive, by returning the same answer as the original function, or having the same side effect, whatever it is that our tests are looking at. To determine how that happens for a given mutant, it helps to take a closer look at the change the mutant is based on, plus at least one test that it passes. So let's start with the plus mutant. Looking at the change together with the test makes it pretty clear that this one survives because 2 plus 2 equals 2 to the second power. And so does 2 times 2, but he's in the background. We can save him for later. So how can we kill this mutant? In other words, make at least one test fail when run against the mutant that would pass when run against the original function. What we need to do is make at least one test use inputs such that x plus y is different from x to the y. And there are lots of ways we could do that. For instance, we could assert that 2 to the 4th power is 16. All the mutants that our original test killed, this would still kill. But furthermore, 2 plus 4 is 6, not 16. So this kills the plus mutant. You see how that works? And seeing some nods out there, seeing some heads not nodding. Don't worry, there will be another example. Better yet, though, 2 times 4 is 8, which is also not 16. We developers should certainly know our powers of 2 at least that well. So this also kills the times mutant as well. You'll often find that killing one mutant kills a lot of others of the same function. But the pair of argument swapping mutants still survive. That's not terribly surprising because 2 to the 4th power and 4 squared are both 16. But we can attack those mutants separately. No need to kill them all in one swell swoop and be some kind of superhero about it. To kill the argument swapping mutants, we can, again, either add a test or adjust our existing test to something like asserting that 2 to the 3rd power is 8. Oops, sorry about that. 3 squared is 9, that's why I was thinking of 9. So this kills the argument swapping mutants. Better yet, 2 plus 3 is 5, 2 times 3 is 6, and both of those are, guess what? Not 8. So the plus and times mutants stay dead, even if this were still our one and only test. In other words, if we had just been changing this test all along rather than adding any new tests. So with these inputs, the correct operation is the only simple common one that gets us the right answer. This isn't the only solution, though. Even if we stuck to single digits, there are lots of ways to skin that flurkin. Now, this may make mutation testing sound simple, but this was deliberately a downright trivial example. So let's look at a more complicated one. Suppose we have a function to send a message, like so. Send message uses send bytes to send as many bytes as send bytes could send, kind of like a woodchuck, looping over and over to pick up where it left off until the message is all sent. Now, a mutation testing tool could make lots and lots of mutants from this, but one of particular interest would be this, an example of removing a looping control. Now, suppose that this mutant does indeed survive our test suite, which consists mainly of this. There's a little bit more that I'm not going to show you quite yet, dealing with setting the size of the message and then actually creating the message. But even without seeing that, what does the survival of the non-looping mutant tell us? If code that only goes through our loop once acts the same as our normal code, as far as our tests can tell, then our tests are only making our normal code go through that loop once. Okay, so what does that mean? You'll find that interpreting mutants often involves a lot of asking yourself, so what does that mean? Often deeply recursively. In this case, it means we're not testing a message larger than send bytes can send in one chunk. There are many ways that can happen, but we're only going to look at two possibilities. The most likely is that we forgot, or more likely just didn't bother, testing with a big enough message. For instance, suppose our maximum chunk size, what send bytes can handle in one chunk, is 10,000 bytes, and yet for whatever reason, we're only testing with an itty-bitty 3-byte message. There we go. The obvious fix is to deliberately use a message bigger than our maximum chunk size. And with the fake messaging we're using here, it's downright trivial to construct one. We just take our maximum chunk size, add some, and make that big a message. But let's look at another possibility. Maybe we did test with the largest permissible message out of a predefined set of messages, or at least message sizes. For instance, here we have small and large message sizes, and we tested with a large, and yet this mutant survives. In other words, we're still sending the whole message in one chunk. What could be wrong with that? What is this mutant trying to tell us? It sounds like a good thing to me. In this case, the mutant is trying to tell us that a version of send message with the looping removed will do the job just fine. If we remove the looping, we wind up with this, and now a lot of other stuff is obviously redundant because we only needed it to support the looping. And if we remove that as well, we wind up with this. And now the message is much clearer that the entire send message function may well be redundant, and we can just use send bytes instead. Now, in real-world code, as opposed to simplified example code, maybe not. Maybe there's some error handling and logging and so forth that we need to have in send message, and for whatever reason, we can't shove it down the stack into send bytes. But either way, at the very least, the looping part was redundant. Fortunately, when it's this kind of problem with redundant or unreachable code, the fix is clear and easy. Just rip out the extra junk that the mutant didn't have. This will also make our code base more maintainable by getting rid of useless cruft that was just getting in the way of understanding it. Now that we've seen some examples of finding both bad tests and redundant code, I'll address a couple of frequently asked questions. First, this all sounds pretty weird, making tests fail to prove that code succeeds. Where did this whole bizarro idea come from in the first place? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 as part of Richard Lipton's term paper titled Fault Diagnosis of Computer Programs at Carnegie Mellon University. The first tool, though, didn't appear until 1980 as part of Timothy Budd's PhD work at Yale. But even then, it still wasn't practical on typical machines of the era, and wasn't practical until about the early 2000s, with significant advances in CPU speed, multi-core CPU, larger and cheaper memory, and so forth and so on. But nowadays, it's practical even on rather low-end, but still modern, systems like this 2020 MacBook Air, almost 5 years old and the lowest of the line. Another common question is, where should we fit this into our development process? Mainly, I think it belongs at least here, as part of the requirements to get a pull request, or whatever your process uses, to be approved to merge into the main branch. You can set some standards for what you're willing to accept, like no surviving mutants on new code and no increase of them on existing code, or whatever you want to do, and sort of ideally ratchet it down. Ideally, this would be done as part of a continuous integration pipeline, started when the PR is created and block it if the criteria aren't met. That said, though, I personally would also do it in the linting stage, where I apply lots of other quality checking tools so my code is nice and clean before anyone else gets to see it. Unless, of course, I've been pair programming, then yeah, they know how sloppy I can get. If you'd like to try mutation testing for yourself, here's a list of tools for some popular languages and platforms, and a few others. I doubt many of you are doing Fortran 77 these days. But don't worry about taking pictures. The final slide has the URL for the entire slide deck. And the tools I know are outdated are crossed out here. There may be some additional ones because I don't know or even follow quite all of those languages and platforms. To summarize at last, mutation testing is a powerful technique to ensure that our code is meaningful and our tests are strict. It's fairly easy to get started with. If we have to annotate our tests, that may be tedious and time-consuming, but at least it should be conceptually easy. But it's not so easy to interpret the results, nor is it easy on the CPU. Even if these drawbacks mean that it might not be a perfect fit for our projects at the moment, I think it's still just a really cool idea in a geeky kind of way. And if you have any questions, we have about 7.5 minutes. And if you think of something later, there's my contact information, plus, as promised, the URL for the slides, complete with a full script, which I've mostly stuck to. So, any questions?
So sometimes surviving mutants can give false positives, right?
Yes.
Like, for example, swapping the input parameters, sometimes that's the expected behavior of a function. So we would maybe also need to check these, or make sure that maybe before the mutation tests are ran, we have this annotated somehow that we expect these mutants to survive, right?
Well, ideally, we wouldn't expect any mutants to survive, but yes, there are some situations in which some little change will produce roughly equivalent code. One of the famous ones commonly used is if you have, checking that x is less than or equal to 10, and it checks that it's strictly equal. Or is it the other way around? One of those two is a common cause of false alarms. Some of the more intelligent tools will analyze the original and the mutant and see, well, with these inputs, that's really saying the same thing, and just discard it. And especially in situations where it's not so dependent on the inputs. Even with that, though, there are frequently a fair number of surviving mutants that are, in fact, false alarms. So in the longer versions of this talk, I sometimes divide it into basically 3 categories: the bad tests or other lack of testing, gaps in the test suite, the redundant, unreachable, or otherwise dead code, and false alarms. There's also, come to think of it, in many programs, quite a lot of code we just shouldn't bother to test, like debugging traces. Fortunately, a lot of the tools give you ways to say, don't bother mutating this line, sometimes this function, class, whatever. But tracking those down can be a little tedious. Did that answer your question?
Yes, thank you.
Thank you.
Any more questions from the crowd? If not, we have 3 questions in the Huva app. So the first one is, how do we decide which parts of our code to cover with mutation tests?
To some extent, it's closely related to the question of which parts of our code do we decide to cover with tests in the first place. I would say the mutation testing tool should be let loose on your entire, at least tested, set of code every once in a while. And when you're writing new code, ask yourself how important it is that this be exactly correct. How important it is that you've chased down the edge cases and special cases and whatnot. Sometimes it doesn't really matter, but if it matters enough to be covered with a unit test or integration test or whatever, it may well be important enough to spend some time running a mutation testing tool on it before you submit your PR.
Great. There's one, it's not a question, rather a statement. It says, I think that the link from the last slide is broken. So.
Oh, okay. Well, let me, can't quite do that while the presentation is going.
Yeah. But yeah, never mind. I thought if you maybe have a quick fix, but yeah, we can move on to the next question.
Yeah, we may have a couple minutes left after the next question.
The next question is, how can we and should we limit the number of mutations if the function is too complex?
Well, if it's so complex that you're having a lot of mutations, maybe reduce the complexity of your function. There are reasons why there are a lot of tools that look for complex functions and warn you about them. And I specifically say warn rather than just tell, because overly complex code, that's not a very good thing. However, some of the tools are, to some extent, adjustable. You can tell them, okay, do this kind of mutation, maybe comment out that one, and so on down the list. That requires, of course, that you dive a little deeper into the theory and understand what the various mutations are doing. And there's even one form called extreme mutation testing, which consists basically of emptying out every function. And this may be doable even in languages where you can't completely empty the function. Maybe you just return 0 or something. And if any tests still pass after that, well, yeah, that's a significant result. That often makes a good, quick first cut.
Yeah, we'll do one more.
Okay.
There's one that just popped up. Can the mutations derive from other mutants, or do they only mutate the original code? I think that was the question. Or do the only mutate? Yeah, so I'm guessing, I guess it was a typo, but I think you got
Yeah, I think I know what's being asked. Basically, do mutants have only one mutation, or can you mutate a mutant and wind up with more? That is actually somewhat of a debate in the circle of people who actually write the tools and so forth, but generally speaking, you'll only have one mutation per mutant. If you allow multiple mutations, the number of ways a function can be mutated, basically, you get a geometric explosion out of it, and that'll make it take even more time. So sticking with one mutation per mutant has a number of benefits. It's quicker, and you know exactly what your test suite is failing to catch, as opposed to having 2 or maybe more possibilities.
Great. We're running out of time, so Any more questions if you have, please ask Dave in person. And yeah, thank you, Dave.
Thank you.